Well, if you've been following along with this information about K-maps, Karnaugh maps, right? You may have thought, well, this stuff is really cool. I mean, it gives us an opportunity to go from a truth table to a most simplified sum of products expression. How far can we take this? How large a truth table can we convert? Well, let's stick with 2 dimensions right now. We did this whole thing based on this cell, right? This single cell which represents 1 row of the truth table. So for that cell, it has a specific value for A, B, C, and so forth. All of our input variables define what goes in that cell corresponding to our truth table. Now, the way things simplified was that adjacent cells would represent values that would represent truth tables that differed by just 1 input variable. So for example, it might be that the cell that's directly above us changes A. So we have A equals 0 for this cell and A equals 1 for the cell immediately above it. Everything else stays exactly the same, and hence A drops out if we compare those 2 cells together. And maybe below we can drop out B. Okay, so A stays the same going to the cell below it, but B changes maybe from a 1 to a 0. All right. C, who knows? Maybe C would change going to the left, and D changes going to the right. There's no more sides. There are just 4 sides to this square cell, so there are just 4 cells that can be neighboring it directly to represent changes in A, B, C, and D. If you wanted to go to 5 variables, well, if you're going to stick with this 2-dimensional representation, can't do it. You actually have to go into 3 dimensions. And so maybe E is coming into the board and F is going away from the board. So in 3 dimensions, we can do 6 variables. How about 4th dimension, time? Well, then we could do G and H. But the point is that when we're going to stick with 2 dimensions, we're going to just have the 4 variables that we are modifying, or 4 input variables that can change to bring us from cell to cell to cell in this Karnaugh map. But all we've done up to this point is a 3-input variable Karnaugh map, which gave us 8 cells, and that was a rectangle that was a Karnaugh map with 2 columns and 4 rows. Let's do a 4x4 Karnaugh map. Now, I debated about putting this truth table up before I recorded so that you wouldn't have to see the process of me writing all those 1s and 0s. But let's go ahead and, well, let you participate in the joy. How about we create this little truth table, A, B, C, D. 4 inputs. 16 possible patterns of 1s and 0s. 8 of them start with 0. 8 of them start with 1. All right. Now, second column, 4 zeros, 4 1s. 4 zeros, 4 1s. Then the C column, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. And then the last column for D, we alternate 0, 1, 0, 1, 0, 1, 0, 1, all the way down. All right. Now, what about our X? What is X going to look like? Well, for X, why don't we do, let's see, how about 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0, 0, 0. Wow, that's a lot of rows. We're going to need a 4x4 Karnaugh map. 4x4, 16 cells. And the way we're going to do this is we're going to have 4 rows, and the 4 rows are going to be identified by the patterns of 1s and 0s that are taken on by A and B. So this is 0, 0, 0, 1. Remember our gray code, 1, 1, 1, 0. Now, instead of having 2 columns like we would have with the 3-input Karnaugh map, we're going to have 4 columns in order to take into account the values for D. So we have C and D that are going to label the columns. So we have 0, 0, 0, 1, 1, 1, 1, 0. All right. Now it's just a matter of mapping those ones and zeros over there. If I were a nice instructor, I'd do this real quick for you. Fast forward through this. Nah. Let's go ahead and copy them over one at a time. This cell right here, for A is 0, B is 0, C is 0, D is 0. That's the top row. That 1 from the top row goes into that cell of the Karnaugh map. This cell right here, 0, 0, 0, 1, it's the second row, which has a 1 from the truth table. So we put a 1 in the Karnaugh map. This cell right here, 0, 0, 1, 1, that hops down to the fourth row. Remember, our gray code makes it so that we hop down. We have some funny hops as we copy through the Karnaugh map. That cell gets a 0. Then the last cell of the top row, 0, 0, 1, 0. This is the third row, so we take care of that cell, that row in the truth table that we jumped over. 0, 0, 1, 0. It has a 1 in it. All right. Now, second row, this first cell, 0, 1, 0, 0. 0, 1, 0, 0, that's our fifth row. We have a 1. The next cell, this cell right here, 0, 1, 0, 1, that takes us down to the sixth row, 0, 1, 0, 1, where there's a 1. The next cell, 0, 1, 1, 1, jumps down to the eighth row, 0, 1, 1, 1, there's a 1 in it. And then the last cell of that row, 0, 1, 1, 0, we jump back up to the seventh row, 0, 1, 1, 0, has a 1 in it. Now, some of you are probably looking at this and saying, you know, Karnaugh, these four rows, they all correspond to A is 0, B is 1. So all of the A is 0, B is 1 rows are right there. All four of those have 1s in it. Why didn't we just copy down 1, 1, 1, 1? Well, we could have. But I like to make sure that everybody's aware of that weird little function of the gray code that makes it so we skip and jump back and forth in the Karnaugh map, or in the truth table when copying it to the Karnaugh map. All right, 0, 0. Oh, sorry. This cell right here is A is 1, B is 1, C is 0, D is 0. That takes a big jump, takes us all the way down to this row, 1, 1, 0, 0, where we have a 0 in it. This cell right here, 1, 1, 0, 1, takes us down to the 14th row, 1, 1, 0, 1, has a 0 in it. This cell right here, 1, 1, 1, 1, jumps down to the last row, the 16th row, 1, 1, 1, 1, has a 0 in it. And then this last cell in the third row, in the last column of the third row, 1, 1, 1, 0, takes us back up to the 15th row where there's also a 0. And so you could have also said, okay, Karnaugh, that third row, that's all the values for A equals 1, B equals 1, which are limited to these last four rows, and the output on the truth table for those last four rows is all zeros. Yeah, we could have just copied it straight, copied the 4 zeros right across that row. But like I said, we're just getting used to this gray code stuff. Now, this row right here on the Karnaugh map, the 1, 0 row, the row where A is 1, B is 0, these four rows right here from the truth table, we're going to copy those across. So this cell is 1, 0, 0, 0. That's the 9th row, gets a 0. This cell right here, 1, 0, 0, 1, gets a 1. This cell right here, 1, 0, 1, 1. We jump down to this row, 1, 0, 1, 1, where there's a 0. And then this last cell is 1, 0, 1, 0. That's this row right here, where we have a 0. All right. Now, like I said before, this particular Karnaugh, well, not this particular, every Karnaugh map, the Karnaugh maps contain exactly the same information, or contain all of the information that's provided by the truth table. But they contain an extra bit of information. It's the pairings, it's the neighboring 1s and 0s, right? So this truth table is actually redundant. All the information that's in the Karnaugh map or all the information that's in the truth table is already contained in the Karnaugh map. So let's go ahead and just give ourselves some room by erasing this truth table. Now it's time to make rectangles. Now, remember, there were 6 rules about making rectangles. We had one rule that said that all the rectangles, once we finished making our rectangles, every single one that's in the Karnaugh map has to be covered. Another rule was the size of every rectangle had to be a power of 2. So we could have a rectangle of size 1, of size 2, of size 4, of size 8, of size 16. Of course, size 16 there means that all of the cells have 1s in them, right? But the size of the rectangle has to be a power of 2. Third rule, rectangles may overlap, but every single rectangle must have at least one cell that's unique to it. Another rule, all the cells in a rectangle must be 1s, because remember, each rectangle corresponds to a sum of products expression, and that sum of products expression is going to generate a 1 for all those rows of the truth table. Rectangles can overlap from one edge to the other edge, or from left to right, or from top to bottom. So the rectangles can overlap, can go across boundaries. So let's go ahead. Oh, and the last rule, and this is the rule that makes it so that the resulting sum of products expression is the most simplified sum of products expression we can come up with. Every rectangle must be as big as possible. So let's go ahead and make some rectangles. First of all, you see this one right here. That one, we can make a rectangle out of those two. Neighboring rectangles, I doubled the size, one variable is going to drop out. Is it as big as it can be? Well, not yet. I can't go up across boundaries because that 0 is blocking me, but I could pair it with the ones below it. And so those 4 can actually make up a rectangle. And by making that rectangle, I actually cover up 4 of the 1s. So there's 4 of the 1s taken care of. And it's taken care of with one product. And since I doubled twice, 2 variables are going to drop out of that sum of products expression. Or excuse me, out of that product. All right, so we go over here to this one. I can't pair it with the one to the left, but I can pair it with the one below. So those 2 can be paired together. Those 2 can be paired together. Can I make it any bigger? Well, it turns out I can't go the whole column because these zeros are blocking me. I can't include those zeros in a rectangle, but I can wrap around to the other side. Let's see what we can do, what color we can come up with for this one. All right, so this is another rectangle. Now you look at this and you say, well, why didn't you just include all of those 1s in a rectangle? Well, you couldn't because that's not a power of 2. That would be 6 cells. If we had had a 1 here, I could have made an 8-cell rectangle, but that 0 right there is forcing me to break that into 2 4-cell rectangles. All right? All right, the next one. I've got a 1 that's uncovered right here. What's the biggest rectangle I can make out of it? I can't pair it with the one above it, can't pair it with the one below it. I can pair it with the one next to it, right? It's overlapping, but since I have that one unique cell, we're okay. Turns out I could actually make it that whole row, and I can get another 4-cell rectangle. All right? And then the last one. There's one more 1 there. I can't pair it with the one to the left, can't pair it with the one above it, can't pair it with the one to the right. But I can cross boundaries and I can pair it with the one below it. So I have one more rectangle right there. And that's all the rectangles for this Karnaugh map. All the ones are covered, right? All the rectangles are as big as they can possibly be. Yes, some rectangles, all of the rectangles overlap, but every rectangle has at least one cell that... But does it? Wow, we actually have a redundant rectangle. You notice this rectangle right here. That rectangle right there, well, these 2 ones right here are covered by this rectangle. These 2 ones right here are covered by this rectangle. This one rectangle is needed because we got to cover that guy, right? wow, it looks like this rectangle right here, and I'm not going to be able to erase it, but you can see this rectangle right here is redundant, and we do not need it. Should have anticipated having to erase that a little earlier. Yeah, I knew it was going to go, but now you can see all the ones are still covered. I was able to remove a rectangle and all the ones are still covered. Makes it for a simpler expression. Now, how many products am I going to have in my sum of products expression? I'm going to have one product for this rectangle, one product for this rectangle, and one product for this rectangle. That's 3 products. If I had not gotten rid of that one rectangle, I would have had 4 products, and it wouldn't have been the most simplified sum of products expression possible. All right? So, what are our 3 products? Let's do this. Let's start out with this one that is going across from left to right in those top 2 rows. Now, to figure out what product is going to be represented by that rectangle, well, there's a couple of ways we could do this. The first way I'm going to do this is really it's a good way if you're just getting started with Karnaugh Maps. It's a good way to kind of get to feeling how these rectangles work. So this top cell right here is 0, 0, 0, 0. This bottom cell right here is 0, 1, 0, 0. So we already see B is going to drop out because B clearly doesn't matter, right? Now we go around to the other side. This cell right here, 0, 0, 1, 0. And this cell right here, 0, 1, 1, 0. All right. Now, what I'd like for you to see is that we've enumerated all the cells for this particular rectangle. And we see clearly B and C are the ones that are changing. Those are the ones that are going to drop out. But let me show you. We start out, B and C are 0, 0, and then there's a row for 0, 1, and then there's a row for 1, 0, and 1, 1. Every possible pattern of 1s and 0s that B and C are capable of, they're right there. So they are not needed. Another way of saying this is that as long as A is a 0 and D is a 0, B and C can be whatever they want to be. And so the product is just going to be A ANDed with D. Almost. What does A have to be? Well, A has to be a 0. So what you're saying is not A. And what does D have to be? Also has to be a 0, so not D. So the product, A bar and D bar, takes care of this rectangle right here. All right. Now another way of doing this is we could have seen that, okay, this rectangle crosses the top 2 rows. What's different between the top 2 rows? B changes. So you can see B is going to drop out. A stays a 0. There's your A bar. What about the columns? It spans 2 columns. One column is C and D is 0, 0. The other one is C and D is 1, 0. So C is going to drop out because that's what changes between the first column and the 4th column. So we can see that B and C are going to be the ones that drop out of that expression. All right, let's do another rectangle. Let's take a look at, this horizontal one, this row. I'm going to try and see if I can't make some room here. And we'll do the same thing. We'll do A, B, C, D. Now, that row, now if you see this, that's great. That means you're on the road to being able to solve Karnaugh Maps without any problem. This row crosses every possible pattern of 1s and 0s for C and D. So guess what's dropping out? C and D. A and B, it doesn't change. It stays exactly the same. So what we've got is A is 0, B is 1, and that's going to be our product, A bar B. But let's go ahead and see by enumerating the list of cells that this guy covers. So the first cell right here, we have 0, 1, 0, 0. The next cell we have 0, 1, 0, 1. Next cell, 0, 1, 1, 1. And the last cell, 0, 1, 1, 0. And we see that, in fact, yes, C and D go through every possible pattern of 1s and 0s. They drop out, leaving us just with A ANDed with B. There's our product. What gets inverted? There's A right there. It's a 0. A's got to be a 0, so you invert that. B, it's a 1, so it doesn't get inverted. So A bar B, that's our term for that row. And we've got one more rectangle. For A, B, C, and D. This rectangle right here, we've only got 2 cells. We're only going to have 2 rows. So only one variable is going to drop out. This cell right here is 1, 0, 0, 1. This cell right here is 0, 0, 0, 1. What drops out? Well, it looks like A is the only thing that changes between the top row and the bottom row. So it's going to drop out, leaving us with the term B ANDed with C ANDed with D. What needs to be inverted? Well, B needs to be inverted and C needs to be inverted, and there's our product. So that horrible truth table that I drew up there at the very beginning, well, it was pretty easy to come up with an expression for it. X is equal to A bar and D bar, ORed with A bar and B, ORed with B bar, C bar, D. And there you go. There's the expression that took care of that truth table at the very beginning. Now, some of you may look at this and say, look, I can pull an A bar out of the first 2 terms. No, don't. And the reason you don't is because, once again, this is a sum of products expression. And the thing that was cool about a sum of products expression was that it was fast, it was efficient. There were only 2 layers of logic. You know, yeah, we had some inverters, but we had a row of AND gates that we went through, and then the output of all those AND gates went through a single OR gate. If you pulled the A bar out of this, you couldn't simplify any further. You'd have A bar ANDed with D bar or B, and that would give you a 3rd level of logic, because that would have to be computed before it then got ORed with B bar, C bar, D. So leave it like that. You're at the most simplified expression for a 4-input circuit.